So in this video, I'd like to go over the surface area of revolution. So the basic idea is that imagine that, so this is the surface area of revolution. So imagine that we have a function f of x, and taken from x is equal to a to x is equal to b. What I'm going to do is take this curve and I'm going to rotate this curve around this x-axis. So this is a rotational axis. So we have a rotational axis and this curve is curved around this rotational axis by 360 degrees. And the question is, the length of the curve taken from x is equal to a and b will create a cylindrically symmetric surface. And I'd like to know, so you got to imagine that this thing is rotated. Every point is rotated on the x-axis, so this whole curve is rotated. And in this case, it looks like some kind of a vase, if you want to call it. But anyway, this curve, right? And I'd like to know what the surface area of this curve is. And the basic idea behind it, we can actually derive the low-level steps, but I'm just going to try to do this really quickly. So imagine that we take a segment from here to here, which is from here to here is ds. The length from this point, it's given by dy and dx, and we'll triangle that element. So here is a piece of the curve, ds, which has got an increment of dx dy. So let's just use Pythagoras' theorem. This segment, right, is, so this point from here to here, right, has a length of y, and that basically is rotated. So it's kind of a ribbon. This ribbon is rotated, and the ribbon length is ds. So here's our ribbon, and it's got a radius of from here to here is y, and this ribbon length, from here to here is ds. So we are expecting the surface, so the surface area element, right, consists of this perimeter, which is 2 pi y, times the length that's being rotated, is ds, which is equal to the differential in the area. So this segment, right, this ribbon area element, I'm going to call it dA. So this is our differential equation that we're going to deal with. And so now we're going to try to convert this in terms of s. So if you kind of remember, ds, arc length of a curve, right, is given by ds squared is equal to dx squared plus dy squared, and solve for ds. And I'm going to try to pull out dx or dy, because if somebody tells you this function is in terms of y is equal to a function of x, it's easy to calculate dy dx. Only for that reason I'm going to solve for dy dx, in which case I'm going to multiply and divide by dx, and you'll be able to see that that's really 1 plus. So our differential equation in terms of the a, right, is given by 2, the differential of the area element, which is the ribbon area, is equal to 2 pi y, and ds is given by the integral, and I should erase this a little bit, it's getting a little messy. dx, so we now have a differential equation. So this differential equation we can multiply by an integral operator because x is going from a to b, so I'm going to multiply by the integral operator x is equal to a to b. So here's our integral operator. Operate on both sides, and I'll write down the answer over here. So, um, so let's just call this area, okay, between A and B, is equal to this, 2 pi y times the square root of 1 plus dy dx squared dx. And so this is the area, the surface area of revolution of that curve. So let's do a quick example. I can pull out the 2 pi, but that's not really relevant. It's not really that important. But let's do an example. And I kind of really like simple examples. So what I'll do is I'll do my standard y is equal to x squared. And I'm going to take it from x is equal to 1 to, let's say, x is equal to 10. And it's not drawn to scale because, anyway, my handwriting is terrible, my graphs are terrible, but hopefully you're learning how to do this yourself. You should be able to sketch out these problems and quickly write down these integral equations. It's important that you derive these equations. Actually, I didn't actually derive this. I should actually go to the low-level details, but I wanted to really quickly do this. But we should be able to derive this very easily. But I just didn't do it. I'm just not doing it in this video. So we're revolving this around the x-axis. So this segment from here is going revolved. So we can just plug it in directly. So the area is nothing more than taken from 1 to 10 of 2 pi y. Y happens to be x squared. And the derivative of x squared is 2x. So that's really 1 plus 2x squared dx. I'm sure we can reduce this, pull out the 2 pi, and if we're lucky, right, we might be able to solve it. And so I won't go through the process because that's not really relevant. Setting up these integral equations and differential equations is what's really important in physics and engineering. So we can actually plug these directly into, so if there is an analytic solution, I would just plug it into Mathematica or Maple or MATLAB or Python with SymPy and stuff, and you'll get yourself an answer. So that's not the important part. Setting up these equations, it's very important that you know how to do this. So I'm not solving the integral, going through the process, but this is basically the surface area of a revolution of a curve.